My name is Caroline Maitre and I will be your host for this event. I would like to thank you all for joining. Today's topic, we will be looking at simulation and virtual commissioning for mixing and filling. Today, I am delighted to welcome our speaker, Mr. Álvaro Cañizares. So I will give a very brief bio and we will be ready to start. So Álvaro started working at Siemens Digital Factory headquarters in Burbank 2 years ago, and since then he's working in an international team at Factory Automation, driving the topic virtual commissioning. He is the project lead for the mixing and filling demonstrator.
So I would like to start with a question this webinar, and the question is an important one: how to handle increased product complexity and shorter time to market. In this case, focus on the food and beverage branch for this webinar, and we are going to focus, for example, in a soft drink use case. So let us imagine that we're all in an important meeting at our company where different departments have been invited to, and we are discussing more or less strategy for next year. We have people coming from the business side, also from marketing, of course, research and development. Engineering teams are also there, and we have invited some production side managers to this meeting. And the first one asking something to the round of participants are the guys from the business side, asking how many products do we need to launch next year, or how many products are we planning to launch next year. Of course, the first one to answer are the marketing team. They have made their research, so at least they have researched at least 70 new products need to be launched next year to keep up the customer demands in established markets, but also to be able to introduce the products of our company to niche market demands. Of course, the other three guys raise their hands to their head, starting with the research and development department, because they know that with the large-scale processes that they have implemented right now in their company, they will not be able to meet these demands and all these new product launches. Of course, they understand that smaller-sized companies are able to keep up this innovation with new products because their production is more flexible. At the same time, we have our plant genius also, despite knowing the problem, and the problem is the scale-up process that we would have to launch all these new products. He's realistic, and he knows that even if we revisit this scale-up process, we would still require a lot of effort, time, resources, perhaps increasing the engineering team, increasing the research and development team to develop these new recipes, also the quality process. And then, of course, the engineering team, which was till now quiet, listening to everyone's issues and feedback, raises his voice. And basically, he sees that the problem that the company has right now is that they're thinking in a traditional way, doing the scale-up process from the lab to the pilot plant, then during production, the commissioning on site, basically spending a lot of time with real production and real equipment. So he asked the round also if we could somehow predict the process behavior and optimize this recipe execution to be able to develop faster new recipes, and also to develop the automation behind the control of the equipment for these new recipes. And this would be possible if we shift the work done during on site at the production with the real equipment to the office, where we can use a simulation-based approach to develop and optimize this recipe, and also a virtual commissioning environment to optimize the recipe execution with the automation equipment. And this is exactly the starting point of this webinar. So we're going to focus on what can be done at the level of simulation and virtual commissioning to optimize all this engineering process. And for that, I would like to start with, or to take for this webinar a small example, a food and beverage example of a soft drink manufacturing, where we have typical processes like dissolving, some pre-mixing of products, further treatment processes, and then we mix together with water in some mixing equipment these two or more ingredients to have a final product reaching the target quality, and then some additional units to storage this finished product, and then in the end we have a filling station or a filling line to fill the finished product in the bottles. So in order to base this webinar on something tangible, we have developed a demonstrator that is based on a simplified view of this process that you can see here right now. And we are going to see how we can solve issues during design and commissioning with a simulation-based approach. So how can we do that? And this is exactly the value proposition. How can we combine tools in order to reach this target of shifting some of the workload to the office? So first of all, we need a systems level engineering simulation. So we need to be able to simulate the different equipment units that we just saw in the simplified soft drink process at a system level, where we can also analyze the interaction between equipment units in order to try to understand how this equipment is working, try to reduce the cost of the equipment by correct sizing of the different parts of the equipment. And how can we also reduce the trial and error phase and also the scaling up process? For example, checking a scenario like what happened if with equipment I want to now start producing double the double of the quantity that I'm producing right now, or double so fast as before. And also, of course, for some parts of the process, we cannot use only system level simulation. So we will need some parts, for example, mixing processes, where we need to go with computational fluid dynamics to simulate the behavior of liquids being mixed, and also coupling this with design exploration, because we are still not sure what are the conditions, for example, for this mixing processes. So we can combine these two kinds of simulation, and then linked it also to the automation, because in the end, in the automation is where we have the recipe execution and the parameters to execute these recipes. So we need to be able to link the automation code to the system engineering, because it's where we have the simulation of all the equipment and all the line, in order to debug the automation code that the automation engineer has programmed to execute the recipes, to avoid delays during commissioning on site, because he is able to test this at the office with a computer, and also later if he has time to debug and increase the quality of the code, this will yield to decrease in unwanted behavior during operation, because more scenarios could be tested before. And this is what we will call the digital twin of our batch production line that I just showed. And I'm going to go into details about different use cases for these cornerstones that we have in this diagram. So right now we're on the bottom left of the corner. So I will start with the system level simulation, where we can analyze, for example, the equipment to choose the correct size of the equipment. We have there at the bottom right an example of the dosing system, where we are dosing some premix, that it can be, for example, some sugar syrup and treated water. We need to be able to understand how this dosing equipment is behaving. If maybe in the next 3 months I need to dose a fluid that is double as dense as before or viscous, I also need to understand if the equipment that I have now is powerful enough, for example, the pump and the motor, powerful enough to pump this liquid that is now twice as dense, even meeting the production requirements that we have. I want to be able to analyze, for example, maximum flow and pressure of my system. And also, if I'm able to scale up production, for example, now I'm dosing 100 liters per minute. With the equipment that I have, am I able to dose 200 liters per minute? And in order to show you an example of how can we use some tools in order to provide this analysis, I'm going to go out from the presentation mode and introduce you to the demo that we have prepared. So now you should be seeing my screen, and what you're seeing there is the tool Simcenter Amesim, where we have this system level simulation. As you can see, it's similar to the diagram that I showed you before. We have different subsystems of the batch production line. We have some dosing lines for syrup and treated water. They are pumped into some mixing units. It's a batch process, so we have here, for example, 2 mixing units in parallel. And then once the product is mixed, is finished, the mixing process is finished, we pump it to some storage tanks, and then finally we have the supply and the filling station with 10 valves in parallel. So this is a system level simulation where we have modeled, for example, the electrical and mechanical behavior of some motors, the pump, different valves for the routing into mixing tank 1 or 2, and where we can also define fluid properties, like for example here for syrup and water, and we can change these properties fast in order to analyze different scenarios. In order to control this production line, we have a TIA Portal project. So TIA Portal is the automation framework that we're using for this project, where we have developed the control for the plant with different sequences, for example, for the dosing. And then what I'm show you today is a software in the loop example. This means that I am running everything on a single computer. This means I'm running the simulation of the process with Simcenter Amesim in the computer, and in the same computer I have downloaded the code that I have programmed for my process to PLCSIM Advanced, which is the virtual controller for the S7 1500 PLC series from Siemens. And as you can see here, we have a running PLC, a running virtual PLC, where I have already downloaded code to save some time. So the PLC is up and running, ready to be connected to the simulation. Also, in order to control this production process, we have a small HMI to interact with the process and, for example, to start the recipe-based execution of the production that I will start in a second. And finally, once we have downloaded the code to the virtual PLC, we need to be able to link the PLC signals, the command signals to the simulation in Simcenter Amesim. So the signals that we're exchanging with the PLC are connected to this block that you can see here. We have several signals that are being exchanged by the PLC. It's mainly signals, sensor signals coming from the simulation, for example, pressure and flow. And coming from the PLC into the simulation, we have command signals, for example, to switch on and off pumps, or the command signal for regulating valves, for example, for the dosing valves. And here we have Automation Connect, is the central interface to connect Simcenter Amesim to automation. In this case, as you can see, we have connected the Automation Connect to the Simcenter Amesim model. So you load the project, and then it reads in and outputs. and then we have a tab for PLCSIM Advanced, where you can see we have connected to the running instance that I just showed you before mixing. And then you need to map variables between the two systems. So now we're ready to start the simulation. So I go to the Simcenter Amesim tab and I click on Start. So now we can see here the simulation is running, and I can start the execution of the recipe. And I can go to the overview to see what is the feedback of my plant. So now we can see here that, for example, we are dosing water. The set point is 200 liters per minute, but there is an issue because we're only reaching 175 liters per minute. Now we can make some kind of root cause analysis to try to understand where is the problem here. Of course, if I'm the design engineer, I'm going to say that the automation engineer has a problem if they're in their control. So I'm going to stop for a second the simulation. And I'm going to investigate in the model where is the issue. So the issue is that we are not meeting the flow requirements for water in the dosing system. So I'm in this part of the model. So this is the dosing system for water. In the end, we are regulating the flow of the water with a regulating valve that is represented here. And the signal to open or close this valve is coming from the PLC. So I'm going to plot what the PLC is sending us. And as you can see here, the PLC is completely opening the valve because he sees someone has set the set point to 200 liters per minute, and the closed loop feedback is not reaching 200 liters per minute, so it's opening completely the valve. So it looks like the automation is done correctly, and the problem is perhaps in the sizing and the configuration of my equipment. So this is an easy example. So of course I know that the flow that I have in my dosing system, that I can also plot here as well, is closely linked to the speed of the pump. In this case, we have a centrifugal pump that is moved by this motor, and we have some fixed speed configured for this pump. In this case, is set to 2000, so probably if I increase this, I will be able to meet the flow requirements. So I'm going to increase it to 2,500 revolutions per minute. And I'm going to update the simulation with this new value. I'm going to reset also the control as well on the HMI. And now I will start again the simulation. And set again the same order for the recipe execution. So you can see here the control is now done properly, and we're reaching the 200 liter per minute set point. I can also go back to Simcenter Amesim and plot the results. So as you can see now, the PID control that we have on the regulating valve is opening the valve to 80%. And we are reaching the set point that was set by the PLC for this recipe. There was 200 liters per minute. So this was a small example how you can use this software in the loop setup to track issues that might be coming from the design of the system or from the automation control. I will stop the simulation because now I'm going back to my slides. So we just used Simcenter Amesim in connection with automation to do system optimization and track issues. But in an earlier stage of the project, you can use Simcenter Amesim for the development of the concept and the design of subsystems, for example, the filling subsystem. analyze the system to find the correct sizing of the components and reduce the cost by oversizing different parts of the system, analyze in time and frequency domain the system, and also once the concept is finalized, you can use it to optimize the system design and have a final model like the one you can see on the bottom right, focuses on the whole scope of the batch line. But now we have other parts of the system that cannot be simulated by Simcenter Amesim. For example, the mixing process. We have a mixing process where we have some sugar syrup that is being mixed together with water. We have two kinds of issues. If we are designing perhaps maybe a new batch line, we can have the issue that we don't have a mixer yet, and we know what are going to be the ingredients that we are going to mix, but we are not sure how the mechanical design of the mixer should be in order to have, for example, an optimized mixing time. This would be called a design exploration, so it would be used in order to, for example, choose the correct number of baffles here around the mixer to set the right shape of the blades in order to mix, in this case, water and syrup. Or it can also be that we want to do condition exploration, for example, for a fixed geometry. I have a fixed equipment and I'm changing the ingredients. I want to know how can I adapt my control. For example, how fast do I need to turn this mixer shaft in order to have an optimum mixing time. This way we can also reduce trial and error phase and product waste by replacing real trial and error scenarios by simulation. I'm going to show you now an example of the optimization of recipe execution using Simcenter STAR-CCM Plus. It's a tool to run computational fluid dynamics simulation. So we're simulating this small mixing equipment, and we have two scenarios. On the left, we have already dosed water, and we're pumping the sugar syrup. We're mixing with a fixed speed of 150 revolutions per minute, and we start mixing as soon as the syrup is added. And then on the right side, we have the same starting conditions. The water is already there, and the syrup is being pumped. Same speed, but we wait for the mixer to start. I'm going to play them now in parallel, so you can see the differences. So the red fluid is the sugar syrup that is being pumped. And what we were able to identify with the simulation is that because of the position of the pipe on the top, we are also adding a lot of air to the mixture. And as you can see there now on the left side, when we start pumping, we have some green dots. These are air bubbles that prevent us from mixing properly and reducing the mixing time. They are playing against us. On the other side, we waited for the air bubbles to go out of the mixture and then start the mixing process. So the situation at the beginning was that if we start mixing, as soon as syrup is added, we had a high volume of air trap inside the mixture that prevented us from achieving the desired mixture quality in the specified time. So after analysis and interpretation of the results, we included in the recipe a waiting time. So it's just a waiting time after the syrup is added, where we're just letting the air bubbles that were trapped inside the mixture to leave the mixture and then start. So we are adding actually an additional step in the recipe execution, a resting time, and we're mixing some seconds less. So in this case, we're just also minimizing the energy of mixing because we're mixing less time, and we're just adding some rest time to the recipe. And of course, for both simulations, we also calculated the torque that the mixture is applied to the mixing shaft. So we can perform these cases of detail engineering, for example, here for the mixer, with Simcenter STAR-CCM Plus, and we can also combine it with other tools, Simcenter Heats, in order to do some kind of iterative approach. For example, if I'm doing design exploration or condition exploration, I can set some variables and the range of these variables in order to let some cyclic simulations run in STAR-CCM Plus together with heats to try to find the optimal values of these variables according to some target function that can be, for example, in this case, to find the minimum mixing time for my process. So started from the boundary conditions. In this case for us was the water properties, the volume of the water inside the mixer, and the fluid properties of the liquid, of the syrup. That's our baseline design, and with that we can start, for example, a parametric optimization if we're using heats, or just a study of how the mixing process is working at the production scale, instead of running trial and errors with the real equipment. Make some analysis and then optimize the design, which could be the geometrical design of the mixer tank, or optimize the recipe execution. And then last but not least, we are at the bottom of our triangle, where we are connecting our automation equipment to the system level engineering simulation tool. So I am able to debug my PLC code, increase the quality and reduce commissioning on site. I can also start optimizing all closed loop controls because I have a realistic physical feedback of my plant. And I can debug the different recipes and automation parameters to find the best fit control parameters for each recipe and each scenario. So among the things that we can do with virtual commissioning, we can debug the PLC code, optimize the control, and of course, once the system is commissioned, we can use it for operator training to see how the operators react to different conditions, to make them feel more comfortable with the HMI control. And also, in case in the future this batch production line needs, for example, to be extended or needs to be able to produce another kind of soft drink, we could use also this module for retrofit scenarios, where we need to check if the equipment will be able to produce the new product, and also to debug the new changes in the automation code. And this is exactly what I was showing in the first example. I was already running virtual commissioning because I was connecting Simcenter Amesim together with PLCSIM Advanced, the virtual controller, and that was already an example of how can we use the combination of both tools to optimize the engineering. So basically what I just showed you, you had the system engineering level. We were using Simcenter Amesim to be able to simulate the physics behind the process. For specific parts of the process, we can use Simcenter STAR-CCM Plus and Simcenter Heats in order to analyze in detail, for example, the mixing process or other thermal processes. And what we did with interpretation of results from STAR-CCM Plus, we optimized as well the recipe execution in the automation. So the adding a rest time to the recipe execution is something that also causes changes in the automation, and then we were able to debug these changes by combining TIA Portal and PLCSIM Advanced together with Simcenter Amesim and Automation Connect. And a more detailed example, I show you how we simulated the mixing process with STAR-CCM, but I also mentioned that we were also calculating the torque applied by the impeller and the fluids. So what you can do in order to reuse the results from that phase is import it back at the systems engineering simulation in Simcenter Amesim. So you are able to perform virtual commissioning with the imported results of the STAR-CCM Plus simulation. So you can perform virtual commissioning also for the mixer motor in this case of the mixer equipment.
I would like to thank you again for joining. A special thank you to our presenter today, Mr. Álvaro Cañizares. And with that, the session is closed. Thank you.